Yeah, so first of all, thanks to Julia and Luca for inviting me. And also thanks to Puya Hatami and Madhu Tulsiani for the collaboration and the work I'll talk about. So I'm going to talk about algorithmic regularity for polynomials and applications. Yeah, so first I'll introduce and give a brief motivation and background on regularity lemmas you've already seen today. Then I'll talk about our results, which are new algorithmic regularity lemma for polynomials. And then I'll briefly describe an application, which is decoding Reed-Muller codes beyond list decoding radius for certain structured kinds of noise. Okay? And I'll say what this means. And finally, I'll just mention some open problems. Okay. So regularity at a very high level is a notion of pseudorandomness that allows one to decompose a given object into a small collection of smaller objects, and these objects appear random according to certain statistical tests. So we have seen regularity in graphs. Well, by the way, so there's this fine print next to decompose because often there is some error associated with the decomposition, and there can be multiple types of error also associated with the decomposition, but let's leave it at this high level for now. Okay. So we have seen Szemerédi's regularity lemma. So this is the claim that every dense graph can be partitioned into a collection of bounded number of pseudo-random bipartite graphs if you discount a small number of edges in the graph. Right? And here regularity means the following, that for every so if you have a bipartite graph, just to be simple, so a bipartite graph is said to be regular if for any two subsets A belonging to one part and B belonging to the other part, the density of edges between A and B is roughly the same as the density between the two parts as a whole. Okay? So one thing I just want to mention right up front is that this property of regularity, it's not immediately clear that you can, it's not true, in fact, that you can just, so if you are given, let me say it this way. So if you look at this property, right, so it involves going over all possible subsets A and B. So it involves exponentially many choices. So it's very non-trivial to try to frame this regularity lemma algorithmically, in the sense that if we want to actually find the collection of pseudo-random bipartite graphs in polynomial time, then it's not clear from this definition how to go about it. Okay? So Szemerédi's regularity lemma is a cornerstone of extremal combinatorics. There has many applications in combinatorics, property testing, in complexity theory, and it's a very what should I say? It's a type of idea, right, that you can use it to get, you can use it to show that certain kinds of structures exist in a graph, but then it's not immediately clear how to actually find those structures. So the same kind of thing is true also for the Lovász local lemma, where you can use it to make statements about existence of certain structures, but then finding the structure itself is a non-trivial task. So the original proof is not algorithmic, and if you are familiar with the proof of the regularity lemma, it's basically an energy argument. So you find a non-regular pair, a pair A and B which violates this condition, and then once you find it, you use it to refine your existing partition, right? And a certain energy quantity goes up at every time. But then the question is, how do you actually find this certificate for non-regularity? How do you find these subsets A and B, which a priori seem to require exponential time? Okay. So Alon et al., Alon, Duke, Leffman, Riddle, and Euster first considered this problem and gave a polynomial time algorithm. And then there was a whole series of works. Finally, Fisher, Matzlia, and Shapira gave an algorithmic O of n time regularity lemma. I'm not exactly going to state I'm not going to state the exact theorem, but notice that O of n is even sublinear in the size of the graph, which could have n square many edges. Alright. So what I am going to talk about here is concerned about pseudorandomness for functions over finite fields, not graphs. Okay? So we'll be concerned in regularity lemmas for functions which map a vector space over a finite field, fp to the n, to the complex numbers. So let me just establish some notation. So f will always say f is fp for a prime field p. So some of these questions don't make sense for non-prime p, but let me defer that question for now. And then, so we'll use this notation e of x, e subscript f of x, to denote this the exponential function. And then the bias of a polynomial is the expected expectation of the exponential over all x in the domain. Okay? And the correlation between f and g is measured by the inner product function over this field. The correlation, and we'll say that a function is pseudorandom if it doesn't correlate with low degree phase polynomial. So a phase polynomial is an exponential of a polynomial in the classical sense, which maps from fp to the n to fp. Okay? So generally we'll use capital P to denote functions which map to the field, and small letters like small f to denote functions which map to the complex numbers. Okay, so the question is, again, similar to what we did for graphs, is it possible to, given a function, can we decompose it in terms of these pseudo-random functions, with functions which don't correlate with low degree phase polynomials? I'll motivate why this is interesting in a moment, but let's just see that for linear phase polynomials, this is essentially Fourier analysis. So suppose you have a linear polynomial is a function which can be written in this way, lambda I xi, and so let's say p1 is the set of linear phase polynomials. So these are exponentials of these linear polynomials, and so here it's clear that measuring correlation with respect to linear phase polynomials is just the Fourier coefficient. So if you write, so for any function f, if you write f, if you expand out f in its Fourier decomposition, so f lambda hat, these are the Fourier coefficients, and you are writing it in terms of exponentials of linear polynomials, then we can split this sum in this into two. So one consisting of Fourier coefficients which are smaller than some quantity, and the other smaller than epsilon, and the other Fourier coefficients which are larger than epsilon, right? So what this means is that, so the Fourier coefficients which are, so this part, so the function, so this function, right, doesn't correlate with any polynomial, with any function in P1. So the correlation with any function in P1 is bounded by epsilon. Okay? So this uses the orthogonality of these functions. Okay? So this function has correlation at most epsilon with any sum over lambda I xi when lambda is in this sum, and it has correlation 0 for any lambda which doesn't appear in this sum. So orthogonality of these of the linear phase polynomials implies that the left side is pseudorandom. And then also notice that because we have Parseval's inequality, which says that the sum of the squares of the Fourier coefficients is at most 1, we have that the number of, so if each of these Fourier coefficients is more than epsilon, the number of terms here is at most 1 by epsilon square. Okay? So if epsilon is a constant, we have that this is a constant number of, it is a constant size linear combination of linear phase polynomials plus some function which does not correlate with linear phase polynomials. And also notice that this decomposition can be made effective, can be made algorithmic using Goldreich-Levin. So Goldreich, so the celebrated theorem of Goldreich and Levin actually gives you a way to find out the, in polynomial time you can find the Fourier coefficients which are large. Okay. So we want to do a similar thing for higher degree polynomials. So here suppose, so let's say P D is the set of phase polynomials for polynomials which are of degree at most d. And the question is, so this is the question that we'll study, how do we do decomposition with respect to these set of functions, right? So we want to take p at most d to be the set of structured functions, and we want to write our function, so a given function we want to write it as a combination of these structured functions and some pseudorandom part. Okay. So this type of decomposition is required in several problems in additive combinatorics. For example, in property testing, the only tests that are known for some natural properties that are known right now go through this route of decomposing into structured and pseudorandom parts. And they are also useful in many different areas in combinatorial number theory. But the main thing to notice is that, so you can say that we can do the same type of thing, right? So we can try to decompose a given function as a sum of exponentials of polynomials of degree at most d instead of linear polynomials. But the issue that arises is that we don't have orthogonality. So you don't have a unique Fourier expansion as we did in this case, and so you don't immediately get any decomposition theory. Okay. Okay. So the question is, what notion of regularity for polynomials gives near orthogonality? Okay. Gives so ideally we would want orthogonality, but suppose even if we are satisfied with the polynomials being nearly orthogonal, what notion of regularity do we need? So Green and Tau, so we'll give a notion of regularity which was shown to work by Green and Tau for high characteristics, and then Kaufman and Lovett showed the same actually works for low characteristics. Okay. Okay. So before I do this, let me actually make this notion a bit formal. So we are given some function f, and we want to write it in terms of polynomials where these polynomials are of degree at most d. And we claim that it's not true that these are all orthogonal to each other, so there's no unique decomposition. So we want to write it in terms of a collection of polynomials which are orthogonal to each other. Okay. So let's look at, so suppose we have some collection P1 through PC. This is a collection of polynomials of degree at most d. So first let me just establish some nomenclature. So we'll say that a collection of polynomials, so we'll call the collection of polynomials a polynomial factor. Okay? So the degree of a polynomial factor is going to be a bound on the degree of the polynomials in the factor. And then this polynomial factor, it's very useful to look at it as a partitioning of f2 to the n into atoms. Okay? So what this means is that, so once you have such a collection of polynomials, so this naturally splits the domain into atoms such that all the polynomials are constant on each of the atoms. Okay? So we can label one atom by say k1 through kc, and the atom labeled by k1 through kc satisfies the property that this is the collection of all the points such that p1 of x is equal to k1, p2 of x is equal to k2, pc of x is equal to kc. Okay. And then we say that a function is measurable with respect to a polynomial factor if it's constant on each atom of the factor. Okay. So if a function is, so if you can write a function as a function of P1 through Pc, then it will be measurable with respect to this polynomial factor. Okay. So now let me get back to, so recall what we are trying to do. We are trying to define the notion of regularity for a collection of polynomials which assures that these polynomials are nearly orthogonal to each other. So this leads us to this notion of rank. Okay? So we'll say that the rank of a polynomial P is equal to the smallest m such that P is measurable in a collection P1 through Pm of m degree d polynomials. Okay? So in this case, if you have x1, x2 plus x1, x3 and you are trying to measure the rank with respect to d equal to 1, then the rank is 2 because you can write it as a function of 2 degree 1 polynomials. Okay. And the notion of regularity, which was introduced by Green and Tau, was that we'll say that a polynomial factor is regular. So if the so say d is the okay, so it's regular if for any C1 through Cm, okay, if d is the degree of the linear combination C1 P1 plus C2 P2 through Cm Pm, then we want that the rank of this linear combination with respect to d minus 1 be high. Okay? So it shouldn't be the case that it shouldn't be the case that you have a linear combination of these polynomials which is expressible as a function of strictly lower degree polynomials. Okay, and the reason why we are bringing this up is because we have this theorem. So again, Green and Tau showed this over the high characteristic case when the characteristic of the field is greater than d, and Kaufman and Lovett handled it generally. So the claim is that if the polynomial is biased, meaning that the right, so this quantity is at least epsilon for some non-zero epsilon, then the rank is bounded. Okay? So this immediately means that if you have a factor P1 through Pc which is regular, okay? So again this means that any linear combination of P1 through Pc has high rank, then you immediately get that any two linear combinations of these polynomials are nearly orthogonal to each other unless unless you have the same linear combination. Okay? Right? So this should be clear because you are taking so the correlation between this function and this function is exactly the sum of lambda exponential of sum of lambda I pi minus sum of lambda I prime pi, right? So this is some linear combination of the pi's, and this expectation is so if it's high rank, then we know that this bias is small, right? So if the bias is small, then this correlation has to be low.
So here you rank, so because you had rank according to rank sub some number.
Right.
Rank of what of P?
So here this is just one polynomial. So its rank with respect to the degree of the polynomial.
-1.
Yeah, minus 1.
Minus 1.
Right. Yeah. So the way it's defined, so it's with respect to that minus. Okay. Okay. So we have this notion rank, which leads to near orthogonality, and then also there's the other important ingredient that if you have any polynomial factor P1 through Pm, then you can refine it to a regular factor. Okay. So in the case of okay, Right. So if you think back to what we did for linear phase polynomials, there we could actually just use the definition of Fourier coefficients in order to get the decomposition into the sum of linear phase polynomials. But here we have to work in order to get, in order to write a function as a function of polynomials in a regular factor. Okay? And this proof is very easy. I mean, so it's just an inductive proof. So you start with any polynomial factor. So you start with any collection of polynomials, and then if it's not regular, it means that there's some linear combination which has low rank. Right? So you find, so suppose P1 is involved in that linear combination, and without loss of generality, suppose P1 has the largest degree. Okay? And then you can just replace P1 by the collection of lower degree polynomials that the linear combination can be evaluated in terms of. And so here, I mean, so it's easy to show that you get, I mean, so you can run this induction. So each time you are replacing a polynomial by a collection of strictly lower degree polynomials, and eventually this induction stops. But the point is that this process is not algorithmic. So here you need to find, so in order to do this, right, you need to find a low rank collection of, you need to find a linear combination which has low rank. Okay? So you can run over all possible linear combinations, that's fine, because we usually assume, so m is a constant, but how do you actually determine, given a function, whether it's low rank or not? Okay. So we need to find low rank, so this step is not algorithm. Alright. So just to recap, so there is a decomposition for polynomials. So so given any, so I want to make two remarks. So basically what we have shown is that if you start from any polynomial p, you can, and suppose the degree of p is d. So you can write p as, so p is measurable, so you can write p in terms of a high rank collection of polynomials. Okay, so you can start with, the collection of polynomials which is just p, and then you get to a collection of polynomials p1 through pc which is regular and hence pseudorandom. And as we said, so these polynomials are nearly orthogonal. So one can just do Fourier analysis to, for example, show that p1 through pc splits the domain. So if you look at the partition which is given by p1 through pc, it splits fp to the n into atoms which are roughly equal in size. So one point is that this is not algorithmic, because this decomposition into regular polynomials, as we noticed in the earlier slide, is not algorithmic. And the second point here is that we are assuming that p is a polynomial. Whereas if you recall, in the case of degree 1 functions, we didn't have to make any assumptions. So we started with an arbitrary function and we could do the Fourier decomposition. So in the rest of the talk, I am going to stick with polynomials, but I am going to show how to make this decomposition algorithmic. Okay? So we won't get a high rank collection of polynomials, but we'll get something else. But so our notion of pseudo-random regularity will not be what we had earlier, but again it's going to imply that the polynomials are nearly orthogonal to each other. Okay. So before we do this, I just want to make one remark about the proof of this theorem that bias implies low rank. So the first step in both Green-Tau and Kaufman-Lovett is this lemma by Bogdanov and Viola. It says that every biased degree d polynomial can be approximated by a few degree at most d minus 1 polynomial. Okay. Right. So the proof basically goes like this. So recall. So we want to show that if you have a biased polynomial, then it is also a low rank polynomial. So you start with a biased polynomial, then you use Bogdanov-Viola to claim that it must be close to some function of low degree polynomials. Okay. And then after that you refine Q1 through QC to a regular factor Q1 prime through Qm prime. And the main theorem in both Green-Tau and Kaufman-Lovett is that if P is approximated well enough by a regular factor, then it is in fact measurable enough. Okay. So measurable means that it's not, I mean, you no longer just have that P is close to gamma of Q1 through QC, but in fact P is a function of Q1 prime through Qm prime. And this proof uses some strong equidistribution properties which are implied by regularity of polynomials. Okay. So if we want to replace our notion of regularity by something else, then it should satisfy two properties. Okay? So one should be that one remark that I want to make is that this part, the Bogdanov-Viola lemma, this part can be made algorithmic very easily. So the part that given a biased polynomial you want to find a collection of polynomials which approximates it, this part can be made algorithmic. But if we want to make the whole thing algorithmic, we need to satisfy two things. One is that the notion of regularity should imply that the polynomials are orthogonal to each other. So that will imply the required statistical properties that are needed for application. And the second is that we should be able to do this regular refinement, in the sense that we should be able to do this step, that if P is approximated well enough by a regular f for our new notion of regularity, it should still be true that we can claim that it's in fact measurable with respect to that factor. Okay. So let's start with this attempt at regularity. Okay. So this is our new notion of regularity. This is just very straightforwardly. So our first attempt is just tries to measure correlation with, just measures the bias. Okay, so we'll say that a factor is gamma unbiased if its bias is less than gamma of the dimension of the factor, which just means m here. Okay, so gamma is some function which, in terms of the size of the factor. So it's clear that if you have such a polynomial factor which is unbiased, right, then of course you immediately get near orthogonality. That's by definition. So then the question is, and then once you get near orthogonality, you also get these nice equidistribution properties. So then, this is the minimal that we can start with. But then, is it true that this actually suffices, right? So remember what we want to do. Okay, so I'll just skip ahead. So the bad part about this definition is that it's actually not strong enough to imply exact computation of P. Okay? So the proofs by Green and Tau and Kaufman and Lovett require stronger equidistribution properties of the factor, which are not implied just by unbiasedness. Okay. So we need a stronger notion of regularity. And for the rest of the talk, let's assume that we are in this high characteristic domain where the degree is more than the characteristic of the degree is less than the characteristic of the field. Okay. So our notion of regularity will use use Gowers norms. Here's the definition of Gowers norm. So if you have a function from f2 to the n to actually complex numbers, well, let's say r, because we don't have conjugation here. So if to r, then the 2 to the kth power of the Gowers norm is this quantity. Okay? So this is just measuring the derivative of f at a random point in k random directions. Okay. So you are looking at a random k dimensional cube in fp to d and then looking at this quantity. So for example, for u2, for k equal to 2, we have this quantity, and if you actually stare at this hard enough, you will realize that this is just the very related to the Fourier coefficients of f. Okay. Okay. So the so we have these right. So let me say this. Okay. So if you have so if your function f is a phase polynomial of degree at most d, okay, and let me write it. So if you have so suppose this direction is easy. So if you have a function which is correlated with low degree, with polynomials of degree at most d, then it's actually straightforward from the definition of the Gowers norm that the d plus 1th Gowers norm is large. Okay. So Green and Tau and Bergelsen, Tau and Ziegler, for the case when p is greater than d, showed that the inverse is also true, and this is the inverse theorem, that if you have the Gowers norm being larger than some being non-zero, then you also have correlation with respect to some degree d polynomial. Okay. So the reason, okay, and so our notion of regularity will use the Gowers norm. So we'll say that a factor is gamma uniform if it's the case that the ukth norm, okay, of the phase polynomial. So we want that for all linear combinations, the ukth norm should be at most gamma of the of m. So dimension of the factor refers to m, okay, where k is the degree of this linear combination. So this is strictly stronger than unbiasedness, because if the if the kth norm is small, if the kth Gowers norm is small, then the 1th Gowers norm is also small, and that's just the bias of the polynomial. So this is a strictly stronger notion than our notion of gamma unbiasedness, and we'll show that it's sufficient for obtaining algorithms and it's strong enough for our application. Okay. So again, recall that we need to prove two things: that this new notion of regularity, gamma uniformity, first of all, that it allows refinement, that if you have a factor p1 through pm, we can algorithmically find a uniform refinement. And second, we want this exact computation, that if it's true that a gamma uniform, that a degree d polynomial is approximated well by a gamma uniform factor, then also the polynomial is exactly computed by the same factor. And we show that both of these are true. Okay? And this, so the proof of the second part uses strong equidistribution results. We have some new equidistribution results for gamma uniform polynomials. This was shown in an earlier work by myself, Eldar Fisher, Hamid Hatami, Puya Hatami, and Charles Lovell. So we use the techniques here to actually show that that gamma uniformity is also enough to imply exact computation. Okay. So the nice thing about gamma uniformity is that it's very easy to estimate the Gowers norm, right? Because so the Gowers norm is an expectation, and you can sample the derivative at different places in order to estimate the Gowers norm. So this part is the one which, so the exact computation part is the part which requires more work, and and it turns out that the equidistribution which is implied by gamma uniformity is enough to imply exact computation. Okay. So let me turn to applications. Okay. So here is one theorem which is immediately implied by what we have shown. So if you have a biased degree d polynomial, then we get a polynomial time randomized algorithm that outputs a d minus 1 degree factor such that p is measurable with respect to that factor. Okay. So this is immediate. So again, first you approximate p by a collection of polynomials p1 through pm. So this using the algorithmic version of Bogdanov-Viola. Then as we said, there is an effective procedure to refine P1 through Pm to a gamma uniform factor, and this part is also algorithmic. And then finally, once you have that P is approximated by a uniform factor, then we know that it actually also must be measurable with respect to that same factor. Here's a slightly stronger result that also follows using combination of known techniques and what we just showed. So if you have a polynomial which has high Gowers norm, which has high dth Gowers norm, so this is a weaker assumption since the bias is upper bounded by the dth Gowers norm. So then there is a polynomial time randomized algorithm that again outputs a factor of degree d minus 1 such that p is measurable with respect to that factor. Okay. So, so the chain of arguments basically goes like this. So if you know that the Gowers norm is large, this means that the bias of the derivative polynomial is large, and then so this polynomial is biased. So then we can use our result to find degree d minus 1 factor such that this derivative polynomial is measurable with respect to that factor. This can be done in randomized polynomial time. And finally, you use essentially Taylor expansion to deduce that p itself. So if this polynomial is measurable, then you can write p of x in terms of its Taylor expansion, and you can get q by making n to the d many samples. So you can do this in order to also show that p itself. So you can basically find q and add q to this factor that we have, and again refine it if necessary, so that ultimately we get that p itself is measurable with respect to that factor. And finally, let me mention our sort of main application. So this is Reed-Muller codes. List decoding of Reed-Muller, decoding of Reed-Muller codes. So Reed-Muller codes are evaluation vectors of degree r polynomials, so of low degree polynomials. And so we consider the question of decoding Reed-Muller codes beyond list decoding radius. So what does this mean? So we have some string, right? And suppose we know that it's correlated with respect to a suppose we know that we have a bound on the distance between your given string and the Reed-Muller code. So now we can try to and this distance may be quite large. Okay? So it's in fact larger than the list decoding radius. So we want to find out some code word which is close to your given string. Okay? So there can be exponentially many strings in your in the distance given, but you want to find some code word which is within this distance. And so our main theorem is that we can do this for structured noise. So what this means is that if your given string, so if your given word is also a polynomial, so it's a degree d polynomial for d larger than k. Okay, so we are concerned with Reed-Muller codes of order k, and you are given something which is a polynomial of degree d more than k. So if you know that the distance between p and q so if you know that P agrees with Q on at least 1 by F plus epsilon many 1 by F plus epsilon fraction of places, then we can find a degree k polynomial such that find a degree k polynomial Q tilde such that P and Q tilde agree on 1 by F plus delta many delta fraction of places where delta depends on epsilon. The point here is that the radius of the list decoding radius of Reed-Muller codes is 1 minus k by f, shown by Parikshit Gopalan. So the point is that here the distance is much larger. So here it would be like 1 minus 1 by f. Okay? So the distance is much larger than the list decoding radius. Yet we can find some degree k polynomial which lies within that distance. Of course, with this caveat that P itself is a low degree polynomial. And the running time of this algorithm is n to the d, where d is the degree of P. So it could be, there could be an algorithm which runs in n to the k, okay? But we don't have one. So let me just sketch a bit of the proof. So again, you start with this that P and Q agree on at least 1 by F plus epsilon fraction of places, and then so you use Fourier analysis to show that you can convert this to a correlation lower bound. So this is straightforward. So if you know that probability of P equal to Q is at least 1 by F plus epsilon, you can show that there exists some non-zero t such that Tp and Tq is also at least epsilon for some degree k polynomial Q. Okay. So now, of course, we have that. Okay, so if the correlation is large with some degree k polynomial, then the uk plus 1 norm of Tp is also large. So it means that since d is greater than k, the d norm of dth norm of Tp is large. Now we do Fourier analysis on Tp. Okay. First of all, we write Tp using our algorithmic regularity lemma. We write Tp in terms of P1 through Pm, and P1 through Pm is this gamma uniform factor where gamma is chosen to be sufficiently small. And once you do Fourier analysis, so again we have Fourier coefficients. So some of these Fourier coefficients involve polynomials whose degree is at most k, and these are greater than k. And you use the fact that these polynomials are nearly orthogonal to each other to deduce that this. So this part has small uk plus 1 norm. Okay. So again we have degree at most k, and this part has small uk plus 1 norm. Right. Okay. Oh, sorry. So the small uk plus 1 norm is immediate. Okay. So once you get this, then you can use near orthogonality to show that C lambda, there has to be some lambda such that C lambda is large and C lambda lies in this part. Okay. So again, so you know that these are orthogonal to each other, and you also have this information that the Gowers norm of the whole thing is large. And then, okay, so so you deduce that there is some lambda such that C lambda is large, and then you can find it, and then since this is basically Fourier analysis, you can find the large lambda using the Goldreich-Levin theorem. Since C lambda measures correlation with this polynomial, so we know that we have Tp correlates with this polynomial for this lambda, right? And then from there it's right. So once you know that your polynomial Tp So this is a constant multiple of the given polynomial. So it correlates with these polynomials which are of strictly lower degree. Then you can show that basically a constant shift of 1 over t times this polynomial suffices. So the constant shift of this polynomial agrees with p on at least 1 over f plus delta fraction of basis. Okay, so I'll end by mentioning these two problems. So here we looked at so the last application was decoding Reed-Muller codes in the high characteristic case. So it will be interesting to have the same result also in the low characteristic case. And the most challenging problem here is that we assume that the function, that we have a polynomial, right? That p is a degree polynomial. But if you have some arbitrary function, then can you again make this be algorithmic? So this is a very challenging problem because this inverse theorem, so the inverse theorem for the general inverse theorem, not for polynomials but for arbitrary functions, in the high characteristic case uses ergodic theory, and in the low characteristic case also uses techniques which are not amenable to being made combinatorial. So this is wide open at the moment, whether you can do Reed-Muller decoding beyond the list decoding radius for arbitrary functions. And of course, if we have this, then we would really have an explicit algorithmic version of the inverse theorem.
So you have this notion of gamma uniformity,
Right.
which implies low rank. Is the converse also true? I think low rank. Does it imply that? Sorry. Gamma uniform implies high rank.
Right.
Conversely,
So high rank implies uniform.
if you are
If you have
large Gowers norm, then you are low rank. But I think the converse is also true. If the polynomial is low rank, then it has large Gowers norm.
So as far as we know, high rank is a strictly stronger condition. Is a stronger condition than gamma uniformity.
You have low rank when you're correlated with the low degree polynomials.
Yeah.
Then you have.
Right, so then you have high Gowers norm. Yes. Yeah, so it should be equivalent actually.
But maybe not strict. Anyway. It is. I had that conversation with my 2 months ago.
Okay.
But not strict. Not with the same.
Not with the same.
Right, so I think you can detect now algorithmically whether you're low rank or not. Right? Or just use the Gowers norm.
Right. So going through this formulation. But I'm not sure directly whether you can.
I think there's a fairly simple argument here. If you're low rank, then you must correlate with the low degree polynomial. Just
Right. Right. But okay. Okay. Yeah.
Just a comment. The
Right.
list decoding radius for Reed-Muller code, it's not really, it's okay. The thing you mentioned is an upper boundary.
Okay. Yeah. But right. When but there are exponential many. So the point I was trying to make is that there are exponential many points. Yeah.
Can you do randomize your algorithm?
No, as far as I know.
go for it level.
At the expense of running time.
No, but he really you don't really have a general situation because he knows his function is a polynomial, right? It's not a general function.
Okay.
Yeah, there is a possibility, but we don't know.
Everything.
There's a constant degree polynomials, right? So we just evaluate all the coefficients.
Right. So you can explicitly get the polynomial. Right. But then, okay. And Goldreich-Levin step takes.
More questions?